No, relatively speaking, it's actually very recent, less than 2 months.
Yeah, yeah. All right. So we are live. Good afternoon, everybody. Good morning if you are in the USA. Today we have a seminar by Erik Curiel, which we're going to hear about many interesting things, I'm sure. So thank you, Erik, for offering to lead the discussion. Sorry, to lead the seminar. So the presenter will go for about 40 minutes, and then we will have ample time for question and answers, or even we can move it into a discussion format. So please feel free to unmute yourself and ask a question to Erik if it's a short one, like a clarification or a small point, and let's keep the longer discussions, harder questions for later. We'll certainly have time to address all of them. And with that, Erik, I'll give you the stage.
Okay, thank you, Andrea, and thank you to the larger KISS consortium for inviting me to give this talk. It's a real pleasure to see so many, well, little icons of faces of people I know and like so much and haven't seen so well. I haven't seen in so long. Sebastian, I'm looking at you. So I'll be talking today about schematizing the observer and the epistemic content of theories, or getting the laboratory into the theory. This may be a bit more of a purely philosophical talk than many of the KISS talks have been, and perhaps more of a purely philosophical talk than many of you have seen me give before. So we'll see how it goes. I'd like to start, well, first I'd like to start by getting my computer to work properly. Yeah, there we go. I'd like to start with a passage from the novel-length poem Patterson by the great early 20th century American poet William Carlos Williams. I suspect Williams would not have much patience for what I have to say today, but he very often nonetheless seems to me to strike exactly the right note. So Williams says, "The vague accuracy of events dancing 2 by 2 with language, which they forever surpass." Now, that it may not be immediately perspicuous why it is, I think, that this passage is relevant to what I'll be talking about today. But I think if you keep in mind that our scientific theories are human languages, with all of the difficulties and foibles and complexities and subtleties and messiness that accrue to every human language, then I think you'll see why this passage captures so well a lot of what I want to talk about. I will also, before I jump into the meat of the act, so to speak, begin with one other quote. So this is from a paper by Howard Stein, some reflections on the structure of our knowledge in physics. And this, much of what I'm talking about today was in fact in large part inspired by the discussion of this paper in particular, and some of Stein's other papers as well. So, Stein says, "I suggest that the principal difficulty is not that of how to leave the theory outside the laboratory door, the infamous problem of theory-ladenness in trying to test theories, but that of how to get the laboratory inside the theory. Well, how do we do it? For of course we do put theory and experiment in relation to one another. Otherwise it would be impossible to test theories and impossible to apply them. It would also, I should add, be impossible to understand the theory as anything but a purely mathematical structure. Impossible, that is, to understand a theory as a theory of physics, if we had no systematic way to put the theory into connection with observation or experience." And this is exactly the problem I will be discussing today. How it is that we are able to make substantive, physically significant contact between the beautiful, pristine, pure, clear formalism of our theories and the often very messy, almost chaotic, congeries that experiments consist of and gives to us. So I'll first talk a little bit about what a theory is, both on my view, both on the standard view, what I'm going to call the standard view, which I think is in fact not too bad of a misnomer, the standard view in philosophy about what the structure of a theory is, what a physical theory is in its essence, so to speak. And I'll tell you a little bit about my view, which is rather contrary to the standard view. I'll then discuss what I mean by the phrase schematize the observer, and explain why it is that I think the standard view goes wrong in not being able to accommodate this idea, at least not accommodate it in a way that's in the way that's needed. I'll spell out some reasons why, in fact, it is important to be able to do so, to schematize the observer. And I'll conclude with a brief, somewhat preachy valediction. So, what is the theory of general relativity? So, here is one way to make that question somewhat more precise. What is the more or less secure fund of scientific knowledge that constitutes the theoretical and empirical content of the theory? Now, this formulation of the theory, the one that is given in italics, is certainly not a standard formulation of the question in philosophy of science today, not philosophy of science in general, nor philosophy of science, nor philosophy of physics in particular. So, on the standard view, in much, if not most, of philosophy of science in general, and philosophy of physics, I would say in particular, especially since the seminal work of Sufis in the early 1960s, this view presupposes that a theory is characterized in a strong sense by its family of models, where a model is always meant to be something that, at a minimum, captures the essence of a solution to the theory's equations of motion or its dynamical field equations. And crucially, moreover, it is presumed that these models have intrinsic physical significance accruing to their formal structures, independent of any consideration of how the theory is applied in practice in the real world. Although there's always perhaps a vague gesture at possible representational capacities of the formalism as an afterthought. It presumes, in other words, that we can cleanly separate one component of the scientific knowledge the theory embodies, that encoded in the theory's formal machinery, from all the other components, including that involving the practical application of the theory by experimental scientists. Now, this assumption, I think, comes out most clearly in the picture of semantics. Actually, no, I want to say something before that. Yeah. I want to say I don't like a formulation of the question that admits as an appropriate answer such a purely formal structure, along with perhaps the fixing of something like a Tarskian or possible world semantics, or a sketch of representational capacity. Because a formulation of that kind, the kind that the standard view gives us, assumes, with no argument ever given, that it is possible to make a clean separation between, on the one hand, one part of the scientific knowledge, general relativity, say, embodies, that encoded in the pure formalism, and on the other hand, the remainder of that knowledge. And the remainder of the theory's knowledge includes, at a minimum, what is encoded in the practice of modeling particular systems, of performing experiments, of bringing the results of theory and experiments into mutually fruitful contact. And that includes all the inexact mathematical techniques that cannot be formalized, approximative and heuristic techniques motivated by loose physical arguments, and kind of vague principles that are not part of the formalism, and that are justified only by their practical success, including in some real application of the theory in actual scientific practice. Now, I think this assumption comes out most clearly in the picture of semantics, the semantics of a theory that naturally and usually accompanies the standard view. Semantics is fixed by ontology's shining city on the hill, and all epistemology and methodology and other practical issues and considerations are segregated to the ghetto of the theory pragmatics. I don't think we should assume such a clean separation is possible without an argument. I should say, by the way, that what I mean when I say that semantics on the standard view is fixed by ontology. I am not in any way claiming that one must be a realist in any standard sense in order to adopt something like the standard view of theory. Instrumentalist. By ontology here, I mean that the semantics is given by fixing something like a Tarskian semantic, the possible world semantic, a category theoretical structure, something that captures the objects the theory treats, it's supposed to treat, and everything else, and that exhausts a large part, if not the entirety, of the empirical content of the theory, and everything else we can just figure out as we go along to this method. So recall my own formulation of the question, what is a theory? What is the more or less secure fund of scientific knowledge that constitutes the theoretical and empirical content of the theory? If one accepts this as fruitful and interesting formulation, then it becomes plausible that the theory of general relativity, say, does not, and indeed cannot, in any interesting sense, consist of the theory of Lorentzian form manifolds, along with a few interpretive postulates or family of Tarskian models or classical worlds or what have you. Now, it may turn out that in the end, a compelling analysis attempting to answer my formulation will show that in the end, the standard assumption of the clean separation of the relevant domains of knowledge, the theoretical and the practical, the theoretical accruing to pure formalism, the practical just all that other mess. It may turn out that in fact is a good and justified assumption, but I personally doubt that it will turn out that way in the end. I think the interplay between theory and practice, experimentation, observation, modeling, heuristic and approximative forms of argument, reconstruction of data so as to make it amenable to comparison with theory, that comparison itself, the interpretation of the data in comparison, is a far more subtle, nuanced, complex, and rich than we tend to appreciate, especially in philosophy, but I think also in physics, especially in mathematical and some branches of theoretical physics. I'm looking at you people who work on black holes every day, by the way. And in particular, I think the theory and the practice, are really inextricably intermingled in a strong sense. The sum total of scientific knowledge constituted by the theoretical and practical content of the theory, which I'll call its epistemic content, for lack of a better term, essentially includes knowledge we have gained, and more importantly, could have gained only through practical modeling, experimentation, observation, heuristic and approximative techniques and arguments, and in particular, the application of representations and models of such experiments and observations in our theory by use of such heuristic and approximative techniques and arguments that can't be formalized. And it essentially contains such knowledge, moreover, in a way that cannot at bottom be cleanly separated from any knowledge grounded wholly in the theory of pure formalism. And that is why I think my formulation of the question, based on the idea of knowledge, is a fruitful sharpening and refinement of the standard of the way the question is normally addressed. For it is exactly the sum of epistemic content that distinguishes general relativity as a physical theory from a merely mathematical structure, as Stein remarked in the long passage I quoted at the beginning of the talk. I will argue that a crucial component of that content consists in knowing how to, in Stein's phrase, schematize the observer in theoretical representations of experiments, and that content, in fact, cannot be had without models of experiments in which the observer is schematized. Now, I want to emphasize from the start that my conception of knowledge here is not limited to anything like justified true belief, but includes, more importantly, comprehension and understanding of the sort that often accompanies explanatory practice, as well as the practical knowledge and art involved in designing and performing experiments, structuring the results in ways amenable to comparison with theory, and interpretation of those results and interpretation of that comparison. So I've used the phrase schematize the observer several times. I think it is fair to ask what I mean by it. To ease into the discussion, let's begin by thinking about what knowledge it is we actually have of the formalism of our theory. For essentially every physical theory we have, Navier-Stokes theory, general relativity, quantum field theory, you name it. I mean, real theory, not point models constructed to try and simplify something that we can't treat using a full theory. For every theory, we have very little detailed knowledge of the structure of generic solutions. Usually we know exact solutions only under conditions of perfect or near perfect symmetry or some other unrealistic assumptions, two bodies, no external perturbative influences. And then we argue that we can apply such solutions to real physical systems because the approximation is adequate under appropriately controlled circumstances. That is to say, we have no real idea at all, in a representational sense, what the world would be like if the theory were true or largely true of it for any physical theory. And that the phrase that has quotation marks around it, what the theory would be like, is a very close paraphrase of one of the most influential formulations of the idea of scientific realism due to Bas von Frossen. But again, what I'm talking about here does not depend in any way on a commitment to realism or a commitment to instrumentalism, or it doesn't depend on taking any decisive stand in the debate about realism. It's just the idea that on the standard view, to understand a theory, to know the theory, is to know what the theory would be like if the theory were true of it, meaning, again, harking back to the idea that ontology fixes semantics. What objects would there be in the world? What properties would they have? How would they interact? In a way completely divorced and independent of anything having to do with how we actually study those systems. This becomes particularly clear, I think, when one stops to think, to really think hard about the mind-blowing, incomprehensible complexity and richness of texture of real physical systems in the world. My favorite example is this bottle of water here, seemingly in equilibrium with its environment, well, as soon as all the sloshing calms down. We know that we can use thermodynamics, we want to get really fancy, maybe the Euler equations, to model the water in that bottle. And it does it remarkably well. We can use a very, very few gross macro parameters, pressure, temperature, volume, entropy, free energy, to say a great deal of what we want to say about the water as water. But really think hard about what's going on in this water. There are little micro eddies and whirls and vortices that arise from microscopic pressure differentials and temperature gradients. That the temperature, generally speaking, is a little warmer near the glass and a little cooler inside. The interaction of the water, the glass isn't perfectly smooth. The interaction between the water and the side of the glass is really extraordinarily complicated. These surface effects, we have almost no theoretical control over them whatsoever. The boundary between the water and the air, the little bits of schmutz and dust and particulate matter that's falling into the water from the air and that came into the water from the pipes when I filled the water bottle up. So, it's not just H2O, but even at the level of regular chemistry, this isn't just H2O. It's actually an ionic bath of a rather complex mixture of different ionic of different ionic substances. It's H2O not even being a majority, but a plurality. There's also H3O, HO, H, and other, even more exotic ionic combinations of H and O, even not even counting all the, all the non-water stuff in it. And those themselves are mixed up, are arranged in really hyper complex web of symmetries characteristic of the hydrogen bond that is characteristic of liquid water. And that's not even to get to the level of quantum chemistry. And of course, I haven't even mentioned yet the electromagnetic field that fills the room and pervades the water from the light bulb, from my laptop and all the mobile phones around the world, from the power generator down the street, from from sunspots on the sun, from bursts from Sagittarius A star, very weak but still there presumably. And of course, that again is not even to mention all the interatomic interactions that we normally ignore, even when we're trying to do molecular kinetics. It's to ignore all the weak and strong nuclear interactions going on. This bubble of water is insanely incomprehensibly complex. And I think we tend to forget in philosophy and in physics. I think we lose sight of how complex real physical systems are, and what a miracle it is that our almost naively, recklessly simple-minded theories and the childishly sketched models we construct in those theories can still capture them with astonishing accuracy, and do so in ways, moreover, that seem to give us real understanding of the world in a broader sense. And correlatively, we forget how much distance there is between those simple models we actually do know in any given theory and the real physical systems they purport to represent. And so we forget how many of the theory's other models, in the standard sense, would almost certainly do the representational tasks required and prima facie do them better by, for instance, adding ever more finely grained details, if one of those models does it at all. We forget how many of those models that we have no idea how to construct in any way graspable by the human mind, or indeed even how to identify if someone gave us one gift wrap. Because most of the solutions, even to the Euler equation, are functions, we forget, they're functions with no closed analytic form. If you think that's bad, think about general relativity, the class of all Lorentzian form manifolds, all the possible topologies of all form manifolds. That and those in some sense or other are solutions to the Einstein field equation. That's something that is simply not the smallest, most infinitesimal part of that is graspable by the human mind. So in light of my remarks about the paucity of our knowledge of actual solutions to our theories of equations, in conjunction with the incomprehensible complexity of the world, therefore, to accept the standard view of theories, I think is to be forced to accept one of two options. We stipulate by fiat that there's a family of actual, or possible in some sense, depending on your mode of predilection, that there's a family of physical systems that we cannot identify most of them in practice. Those are the ones represented by the solutions, and those are the models. Or we stipulate by fiat that the family of solutions themselves, maybe vector fields on appropriate phase space, that the family of solutions themselves are models, although we cannot represent them, the overwhelming majority of them, in anything like closed form, or even identify almost any of them if they were to bite us on the ass. So call this the standard views dilemma. In both cases, whichever horn of the dilemma we grasp, we are saying that the overwhelming majority of the content of the theory is something that we do not know, are in fact nowhere near knowing, and have very good reason to think we will never know in anything remotely resembling thoroughness and detail. I mean, epistemologically speaking, grasping either horn of the dilemma is, epistemologically speaking, an act of faith. Nonetheless, the story goes, there's this preternatural relationship of subsistence that holds among the formalism, the models, the physical systems that univocally and unambiguously fixes them. And that in turn gives rise to a magical relation of reference or representation that zaps out from the formalism to the world and latches onto the salient physical systems in a physically significant, meaningful way. And we, in our supernal cognitive puissance, just know this. I don't see any other defense the standard view can give for claiming that the theory in its sense is the collection of models. But we are talking here of a Fichtean faculty of pure intellectual intuition that grasps without cognitive or perceptual mediation the Kantian ding on Z. Or more precisely, we are talking of nothing about. And a semantic relation that is not known and cannot be known by humans in our current epistemic circumstances has no possible use in actual science and has no possible bearing on a fruitful and illuminating analysis of scientific knowledge. What we need is a mechanism or a device for bringing a mathematically characterizable situation in the world of experience into substantive, physically significant contact with the mathematical structures of our theories. This mechanism would be an intermediary that identifies the junctions where meaningful connections can be made between the two. And it would embody the possibility of the epistemic warrant we think we construct for our theories from such contact and connection. And that mechanism, I shall argue, is exactly the schematizing, the schematic representation of the observer. So I'll finally tell you what I mean by that. So by schematizing the observer, I mean something like in a model of an experiment to provide a representation of something like a measuring apparatus, even if only of the simplest and most abstract form, that allows us to interpret the model as a model of an experiment or observation. And when I say a representation, even if only of the simplest and most abstract form, think about the representation of the simplest kind of astronomy. You know, when in the 1600s, when Flamsteed and Haley and all those guys were constructing the ephemeres that Newton used in arguing for universal gravity in the Principia, all they needed, they did in fact model the instrument, the telescope, and they did it just by a line of sight, by an angle between the surface of the Earth and the telescope, and what angle that corresponded to, how to translate that angle into celestial longitude and latitude. So, I mean, something as simple as a line of sight can suffice and can in fact do very powerful work. But what's important, what I want to emphasize and argue for, is that this schematization of the observer, even in the simplest of cases, in fact requires all the other components of the practical part of scientific knowledge that the standard view wants to relegate to the ghetto of pragmatics. I'll quote Stein again. In actual fact, the experimental physics is treated separately as a discipline in its own right that is partly an art, an affair of both knowledge and manipulative and perceptual skill. But the possibility of connecting this art with the theory is closely connected with a certain possibility within the mathematical structure that is the theoretical framework. The possibility of representing experiments and of representing the observer schematically. I want to speak of schematizing the observer within the theory. The intention is to secure empirical content within experience, or in an abstract structure. So far as the fundamental theory is concerned, means any good theory of physics really, or rather so far as mathematically defined structures and rigorous arguments are demanded, the schematic representation of observers, experiments, and observations is, I believe, as far as we know how to go. So why do we need to do this? Because on the standard view, recall, constructing models of experiments is a nice and cool and fun thing to do, but it's something physicists do. And it's something physicists do in the kind of work that is irrelevant to the philosophical comprehension and understanding of what a theory is and what the empirical content of a theory is. In fact, many eminent and influential philosophers in the tradition of the standard view will go so far as to explicitly deny the need to be able to construct models of actual experiments. Because, however, the meaning of scientific terms and propositions must rest on the knowledge we have of the physical world, and most of all on the knowledge we have gained through controlled observation and measurement, that is, through experiment, epistemic content accrues to a scientific theory in no small measure through the successful construction of representations of physical systems in the theory's terms. At bottom, then, what secure epistemic content the scientific theory has must rest on the meanings expressed in the sound articulation of experimental knowledge. This requires, at a minimum, that we be able, at least in principle, to construct appropriate representations of actual experiments and observations in the frameworks of our best scientific theories. That is, representations of physical systems and experimental apparatus in relation to each other as required by particular actual experiments, schematizing the observer. Not just representations of physical systems implicated in abstraction from actual experiments as in the standard view. And there are, as I have intimated, several reasons why I claim that schematizing the observer is required for an adequate philosophical analysis of the structure and semantics of theories and of scientific knowledge more generally. And I'll discuss four of them in somewhat more detail. The first two in briefly, the third a little in more detail, and the fourth is really the most important one. The first, as I say, it's a shallow reason, but it's still an important one. And sometimes the nature of the observational process itself results in distortion of the magnitudes measured, and a proper computation of the quote-unquote real values of the magnitudes of the system's properties requires explicit modeling of the interactions between the measured instrument and the system itself to correct for the effect. A very simple example is stellar aberration. When light from a star enters a telescope, the motion of the telescope transfers to the path of the light, while the light traverses the telescope. The motion of the telescope being due to the diurnal rotation of the Earth, the orbital motion of the Earth around the Sun, and so on. This motion makes the star appear displaced from its actual position in the sky. In order to correct the effect, one must compute the actual motion of the measuring device, which requires an explicit representation of it in one's model of the observation. Now, the second reason I think is a middling deep one. Not very deep, but it's deeper than the first one. And that's the quantitative results of all measurements and observations, even the best ones, inevitably deviate from those predicted by theory, even if only by a small amount. Likewise, there's inevitable imprecision in the measured values. So such deviations largely accrue to measurements on account of systematic errors arising from the idiosyncrasy of the particular experimental apparatuses used, the ways they're actually configured and deployed during the measurement process, the way they're put into relation to the system. The imprecision is an inevitable artifact of the limited acuity of any probe. But in order to compute reasonable values, the expected errors and imprecision, so as, for example, to be able to say when a measured result differs by an inadmissibly large amount from a theoretically predicted result, one must often take account of fine details of the measuring apparatus and the particulars of its coupling to the system under study in one's model of the experiment. Now, thermometry provides a really beautiful example. And I mean, I could give a whole series of lectures on thermometry and how it exemplifies this idea. It's beautiful how experimentalists have accommodated the complexities of the subject. But for our purposes, well, it just suffices to note that, for instance, different sorts of thermometers, bowls of gas, pyrometers, and homogeneous thermocouples, and all the rest, they couple the systems in radically different ways. The physical interactions they have with the system that result in a temperature measurement are of radically different kinds. And the fine details of those different kinds of interactions have to be handled on a case-by-case basis in order to correct the effects of such phenomena as convective currents and fluids. So, the way that convective currents and fluids interacts and bears on the proper functioning of a gas bulb thermometer is quite different than how it bears on the proper functioning of an inhomogeneous thermocouple. And if you want to use both thermometers and make sure that both thermometers, are properly calibrated and it will agree with each other, you have to take account of it. So the third reason why I think we need to schematize the observer is a deeper one. Theory must be able to provide guidance to experiments in the design of new types of tools for probing novel sorts of phenomena, and also in the design of new types of tools for probing new phenomena in novel ways. Conversely, experiment must be able to provide guidance to theory in modeling practically constructed novel ways of coupling the systems known and unknown, so as to place constraints on a possible soundness of theoretical description and prediction of it. And in order for each theory and experiment to carry out these tasks, theory must be able to represent the fine details of the apparatus as it actually is to be used in the experiment. And this particular interplay between theory and experiment, in theoretical guidance and the construction of instruments on the one hand, and in experimental constraints on the soundness of theory on the other, is one of the most profound ways that theory and experiment are able to make contact with each other. And without it, it is difficult to see how any epistemic content could accrue to theory in the first place if this interplay could not happen. And the fourth reason is the deepest, I think, and depends in part on the previous three. Without an understanding of the fine details of the way that theories do and do not successfully model actual experiments of the kinds of physical systems that theories purport to treat, we have no way to demarcate the regime in which the theory is in fact appropriate and adequate for representing those kinds of systems, what I'll call its regime of applicability. And it is only by dint of the practical forms and aspects of scientific knowledge, in other words, that we can determine a theory's regime of applicability. When, for example, what we pre-theoretically conceive of as an actual body of fluid manifesting some dynamical behavior, say something like it's approaching turbulence, when that actual system is appropriately and adequately treated by Navier-Stokes theory and when it is not. Now, when I say, I guess I want to say a little bit more about what I mean by saying that about this regime of applicability. So every theory we know of has associated with it characteristics sets of breakdown scales, what I will call breakdown scales. And those breakdown scales come in an enormous number of guises. They can be energy scales, spatial scales, temporal scales. They can be combinations of those. They can be functions of quantities that are peculiar to the type of system at issue. So, when you're doing fluid dynamics, you know that the theory will break down when we start probing the fluid on scales that are a couple of orders of magnitude larger than the mean free path of the molecules of the fluid. We know that if the ambient electromagnetic field is strong enough to ionize the fluid, then Navier-Stokes can't handle it because Navier-Stokes can't handle ionized fluids. We know that in classical Maxwell theory, if the amplitude of the electromagnetic field, begins to approach in an appropriate sense h bar, then classical Maxwell theory breaks down. You have to start using QED. In fluid dynamics again, I love fluid dynamics. It's such a beautiful and rich theory. If the Reynolds number is too high or too low, the Reynolds number being a measure of a characteristic viscosity quantity associated with the fluid and a measure of kinetic energy. If that gets too high or too low, then generally speaking, the fluid theory can't handle it. They're all different kinds of ways in which the way a system is in a particular state and the way that system in that state is interacting with its environment can be such that the theory works well to model it and can be such that the theory completely breaks down and fails to handle it. And all the systems with their states and the states of the environments that they're interacting with, that the theory can appropriately and adequately treat. That's what I'm calling its regime of applicability. The standard view is
Erik,
right.
It's already been 40 minutes.
Okay.
I'll give you 5 to 10 more minutes.
I will only need 5. I will only need 5.
Okay, perfect.
So the standard view gets right. The fact that the family of physical systems the theory appropriately and adequately treats is a central essential component of the epistemic content of the theory. The standard view goes wrong in thinking that it makes sense to characterize this family in the abstract, without recourse to and reliance on all the scientific knowledge we have pertaining to the theory and its application. To identify that family of systems, the ones that the theory appropriately and adequately treats, we need to fix error tolerances, acceptable levels of precision. We need to figure out where these characteristic breakdown scales are in our experimental. We have to do that in experimental practice, because the theory's formalism by itself can't tell you that. But in order to do all that, we need real models of actual experimental techniques representing the actual tools we have at our disposal for performing such measurements, because the regime of applicability actually changes over time with advances in practical knowledge. As you know, with advances in experimental techniques, construction of experimental devices, the improvement of physical techniques for reconstructing data, all of this leads to generally theories being able to treat well larger and larger classes of physical systems. So the family of systems that a theory treats, which is central to the standard view, the semantics is fixed by ontology, is not something that's fixed sub specia aeternitatis. And I mean, knowledge of the regime of applicability embodies perhaps the most important part of the epistemic content of the theory. Without it, we have no warrant at all for trusting our use of theory, much less for understanding it as a theory of a particular class of physical systems. And nothing in the theory's formalism can tell us this about the input of knowledge that can be had only by experimental practices that require schematizing the observer in theoretical models. Now, if demarcating the regime of applicability did not depend on practical knowledge of the kind that changes, the current reach of experimental techniques that determine fixed levels of precision and accuracy, the availability of approximated theoretical techniques and heuristic forms of argument to make calculations tractable and on and on. If the regime of applicability didn't depend on all of that, then there would be a fixed number once and for all. You say 3.141592653558 and so on times 10 to the minus 6 centimeters. At scales smaller than which the representational capacities of Navier-Stokes theory breaks down. But that's just wrong. Navier-Stokes breaks down at different scales for different types of fluids under different conditions, and the increasing acuity and resolution of our measuring instruments, in conjunction with our increasingly powerful control of experimental error, both practically and experimentally, and the increasing sophistication of the models we can construct of our measuring devices, and the fine details of their interactions with different Navier-Stokes fluids under different conditions, all mean that such numbers become ever smaller or larger, depending on what kind of breakdown scale you're considering. As I have already said, they are not fixed sub specia aeternitatis. And thus, neither is the family of physical systems that the theory appropriately and adequately treats, neither is that fixed sub specia aeternitatis. And I think this is right. The scientific theory is not a platonic form. It doesn't exist independently of our actual epistemic state. But recall, in the standard view, this family of systems that the theory is supposed to treat is absolutely central and crucial. All empirical content is supposed to flow from that family of systems, and that family of systems is supposed to be fixed by the formalism of the theory. In virtue, I'll conclude. I'll skip the valediction in interest of time. This is my last slide. I just want to conclude by remarking one further consequence of the arguments I've made, if you accept them. So in virtue of the last two reasons, that theory must guide experiment in design of instruments and experiment on constrained theory and the construction of sound models of systems and the demarcation of the regime of applicability, those two reasons. One cannot even define physical quantities, for instance, temperature, without explicit schematic representation of the observer, much less have understanding of how to employ their representations in scientific reasoning. Without such a definition, however, any theoretical proposition referring to temperature can have no epistemic content. So, thank you.
Thank you, Erik. Please join me in thanking the speaker. And I'm sure there will be a lot of questions. If you want, you could raise your hand using the Zoom interface. Yes, Johannes.
Right. Thanks very much, Erik. Yeah, wonderful talk as always. I was just wondering whether you could give me a little bit more of an idea of what the observer schema or schematizing the observer would be formally. And maybe to just throw in an example, I'm not sure if no problem if you, if that's not a good example. So for example, in psychology, there's a lot of, there are actual nice tools to do that. Like, for example, the one that goes under the name of fundamental measurement theory or axiomatic measurement theory. And I think they would at least share a subset of the things you wanted, like just the words you had on the slides, they use them too. And so my question would be like, would that be an example in case you happen to have seen that before?
So are you referring to the formal measurement theory as worked out by like Supis and Tversky and those guys and their magisterial books on measurement theory?
Yeah.
So in fact, so the kind of stuff that Tversky and Supis and those guys talked about. So I don't know much about psychology at all. So I don't think I can talk about the details of how these things are applied in that science. But the kinds of things that Supis and Tversky and all those guys talk about in the book, that book is that series of volumes. It's a funny piece of work because on the one hand, Pat Supis he was always much more so than his formal writings would lead one perhaps to believe. He was always incredibly interested in what I've been calling the pragmatics of science. His account of models of data is a beautiful example of this. But I wish, hope, very sadly, I can't ask him anymore. I think Pat would have a lot of sympathy with a lot of the things I'm saying here. Not everything, but at least, my discussion really applies to sciences that can, in some sense, be lightly mathematized, so to speak. I know what it means to define a system, define a way of interacting with the system, design an instrument that takes advantage of that way of interacting with the system, and employ the instrument so as to interact with the system in a way that returns information about the state of the system. If you can do that in psychology, then I think that would be an example of what I'm talking about. Whether or not psychology needs that in the same way that physics does, I can't say because I just don't know enough about psychology. I'd be very surprised if it didn't need that, because the little bit of work I know in cognitive psychology and neuroscience, which is almost all having to do with stuff like the entropic brain hypothesis and the free energy principle and IIT and all that fancy jazz. The experiments they do are in some sense so crude and so simple that I don't see how you possibly can try to interpret them as anything but experiments. I think it's incredibly dangerous in a science like psychology, which I consider to still be in its very earliest infancy compared to chemistry or physics, to try and draw larger lessons about systems in the wild, so to speak, from the very kinds of crude experiments and observations that we currently are capable of performing. I don't think I really answered your question. But,
no, I think you did. I think you did. Yeah, thanks very much.
All right, next we have Sebastian. And Erik, would you like to stop sharing screen so we have bigger faces?
Yeah, so I'm wondering, so there's this old adage that if you stand still long enough, fashion will catch up with you again. And
Hey, Sebastian, I'm sorry. Your voice is a little fuzzy. Can you please repeat that?
Oh, that's really odd.
It's good to see my bad hair.
No, okay. Well, so there is this old saying that if you stand still long enough, fashion will catch up with you again, and so I'm wondering a bit how much your position would be supported by something as flat or sort of as old-fashioned as the Duhem thesis, and not Duhem-Quine, but really sort of Duhem with, well, our theories don't actually have any content on their own. We always need these supporting theories that connect them to experience. And once you're there, then it's a small step to thinking of it as sort of reverting, to think of it as saying that, well, we start out with our experience and the semantics sort of seeps from our observations into the theory, sort of what was called semantic empiricism, I think. So I'm wondering whether this is basically that, but presented now with the knowledge that we have about physics and with a new sort of counterposition, namely the model view of scientific theories.
Right. Oh, so good. I really like that question. So first of all, I should say I'm really happy you called it the Duhem thesis and not the Quine-Duhem thesis, or even worse, the Quine thesis, because Quine just got it so badly wrong. But that aside. So I think that personally I have a great deal of sympathy with a lot of what Duhem said. I think I might, and I suspect that there is, in fact, without having thought seriously about this, about this particular analogy or point of contact between my views and Duhem's. My sense is that there probably is quite a lot of overlap, but I think that, I mean, Duhem talked about. I mean, the way that we talk about Duhem today is, the kind of the caricature of Duhem is there are these auxiliary hypotheses, and and you always need that in order to make predictions and use theory to characterize physical systems and all that. And insofar as that caricature is actually latches on to something about Duhem's view, I would say that that is part of what I'm getting at. But to me, I think one of the really interesting questions that if you think something like my view is interesting or potentially fruitful, one of the really interesting questions to ask is where does the theory end? So in astronomy, is the theory of the telescope as an optical instrument, is that part of the theory of astronomy, or is that a separate theory? I think at the end, a lot of these questions would be in danger of degenerating into just argument about words and not get at anything really substantive. But I think there is a substantive question there if we're careful, which is how much do we need to know theoretically about instruments in order to schematize the observer? And as I remarked earlier, in the 16 and 1700s, representing a telescope as a line of sight did the job perfectly. It wasn't until late 1700s, early 1800s that stellar aberration that they began to have to worry about stellar aberration. So, insofar as Duhem doesn't seem to want to, if I recall correctly, Duhem doesn't characterize theories as I am, as a kind of an epistemic cloud. But if I remember correctly, he characterizes them, in fact, by the sets of physical systems that they are intended to and do, in fact, adequately treat. Then if that's right, then I think that where I differ most importantly from Duhem is in my treatment of the regime of applicability, because Duhem never actually says how it is that we ascertain what is the group of systems that we have reason to think our system really latches onto and treats in a physically important and substantive way. But I don't want to go overboard in trying to say I differ. My view is novel and original, and I differ from Duhem in all these ways. I think that there is a great deal of contact and continuity there, and I'm very happy to claim him as a progenitor.
If I can have a quick follow-up. Yeah, well, and I mean it's kind of nice, right? You have a position that is new in the sense that it poses a problem for the standard view and an unobserved identified problem for the standard view, but at the same time it actually is supported by views that are quite generally accepted. No? And one way of seeing this is one way I think how it gets into your theory is when you start talking about knowledge that we have instead of the theory in the abstract. Because then, that's what we teach our undergrads, right? When we test our theory and the experiment comes out wrong, it could be anywhere in the individual, in the steps from the theory to the observation that could have been wrong, right? And when you think of Blanc-Law's N-rays or so, where it was basically we actually have to model our physical visual system to see where this went wrong. So yeah, I think basically it just supports your view. There is nothing wrong with being supported by a good philosopher and physicist, right?
Not at all. I am very, very happy to claim any kind of support like that I can get. Thank you.
Next we have Richard.
Yeah, I have two related questions. The first one concerns the distinction between a particular theory that you're interested in giving meaning to by schematizing the observer, and a whole panoply of other theories that might be required in order to connect that theory to a particular experiment which somehow helps you to schematize the observer. So how do you see the role of other theories besides the one you're trying to give meaning to? In particular, other theories which in some perspectives can be seen to be superseded by the theory that you're trying to give meaning to. To make it more concrete, if you want to give meaning to general relativity by schematizing the observer, is it okay to use Newtonian physics in schematizing the observer, or is that somehow a no-no? Okay, that's the first question. The related question is, how exactly does schematizing the observer contribute to the semantics of a theory? You said a lot about epistemology, and I have a lot of sympathy with the idea that traditional referential semantics and representational approaches to semantics are not the way to go. But I want to see how this new alternative is going to go. How do we get semantics rather than epistemology out of schematizing the observer?
Both excellent questions. So with regard to the first one, I actually the example you gave at the end of the first question is actually one of my absolute favorite ones for challenging people who really like formal epistemology. Because if we couldn't use Newtonian gravity to do GR and astrophysics and cosmology, we'd be dead in the water. Because 99% of astrophysics is done using Newtonian gravitational theory. 99% of the measurements we make are modeled using Newtonian gravitational theory. We better be able to use it, or else when you look at almost all of the evidence we've ever collected that seems to support general relativity, the overwhelming majority of it was collected in experiments and observations that were explicitly modeled using Newtonian gravitational theory, and the systems themselves were partly modeled by Newtonian gravitational theory. And yet we somehow seem to think that we can extract from this the kind of general relativistic part that supports GR. So I think that this to me is actually one of the what I take to be one of the virtues of the kind of picture that I'm trying to push. Because if you think of a theory as a formalism plus some interpretive principles or plus a Tarskian semantics or something like that, it makes no sense whatsoever how this process of using superseded theories to support better theories could possibly work. You can invoke approximation all day long, but as long as your semantics is ontology, it's not going to work. This is why this is my favorite example for use against formal confirmation theory.
Right.
On my view, the knowledge that was part of Newtonian gravitational theory just gets taken up in general relativity. As long as we can show that general relativity can kind of incorporate and digest what we learned from Newtonian gravitational theory and can do it so meaningfully, then the problem is just obviated. So I take that to be a virtue. So I'm not sure if the first question you asked is actually rather complex and seemed to have several different parts. I worry that I only addressed or tried to address one of them.
I wanted to include lots of other theories besides gravitational theories as being required. And when you include that whole variety of theories, in what sense are you simply giving meaning to general relativity rather than sort of moving meaning around amongst this whole slew of different theories?
Right. So if I understand you correctly, you're talking about things like a theory of the telescope. You need optics in order to understand the telescope. You need some meteorology in order to understand how electromagnetic radiation is diffracted and dispersed by moving through the atmosphere, and you need to know all this stuff in order to model a real observation.
Right.
So I think that is in fact a really hard and deep question, and to me that's a really interesting question that I don't have a good answer. I don't have a good answer for you right now. But it seems to me that this is exactly the kind of question that philosophers should be interested in.
Right.
And that the standard view kind of completely obfuscates this kind of question from view. So I take it to be one of the virtues of my picture, that it reveals what I take to be the really interesting, important hard questions that are just completely hidden by the standard view. I don't have a good answer for it. I'm sorry to say. I think it's something I really want to think about and work on more. So the second question, damn it, I've already forgotten. How much words?
I want to endorse your skepticism about referential semantics, but what's the alternative?
Right, semantics. Okay, good. So I actually do have an entire theory. Well, I have almost an entire theory of semantics worked out based on these ideas. Yeah, the idea of what it means for a theory to appropriately and adequately treat a kind of system based on knowledge of the breakdown regime, of the regime of the applicability and the breakdown skills. But I don't have time to tell you what it is right now. But I can send you a manuscript if you like.
I would very much like to see that. Thank you.
Okay.
Chris, next.
Hi, thanks, Erik. So I had a question that was very similar to Richard's, but I might put a slight twist on this, which is to say that there might be a useful contrast drawn between the question of sort of novel fundamental quantities that a new theory introduces in order to formulate laws and how to think about those, as opposed to the sort of long chain of representations that you'd have to go all the way from the theory to, what the actual observer is. So I think there's a slightly separate question, which is at one end, when you've gotten a new theory that says, here's a set of quantities, and then you can maybe try to see if it will connect up with the long chain going all the way back to the observer. And so there might be a separate question there that's interesting. So I'd be interested to hear what you have to say about that. And the other question I had, which is slightly separate, is just, isn't it the case that sometimes theories can sort of internally show us what their regimes of applicability are, that they can show us that they're going to break down? And I'm curious how you respond to that. I mean, it may be that there's the kind of practical knowledge that's implicit in those arguments, but it seems like that's a different style of argument than the one that you're putting an emphasis on. Okay,
good. So I'm going to answer the second question first, because I think it's much easier. So if you're talking about things like, say, effective field theories in condensed matter physics or effective field theories in particle physics, then yeah, these theories in fact are constructed from the ground up, so to speak, to include information about what I'm calling the breakdown scale, and that those are wonderful when it happens. But it's never the case, even for those theories, even for theories like that, where the theory is constructed, from the start to include to make manifest and make explicit where we expect the theory to fail. That never exhausts all the ways the theory can fail. That there are always ways that the theory can fail and will fail. that the formalism simply won't tell you. At least, I mean, okay, I don't want to make an in-principle claim here. I don't want to say that I have, an a priori categorical deduction of this claim. I don't. But it simply is the case that all physical theories that we've ever dealt with in a serious way have this feature, and at least in our current situation, it's hard to imagine any theory we construct not having that feature. But I don't want to claim that it's somehow impossible in principle for such a thing to exist. The first question actually was a little more complicated, and I'm sorry, I didn't quite get. Can you please say again what the distinction is you're trying to draw between why it is that novel quantities? You were trying to compare the how it is that we connect a theory and experiment through long chains that reach back for well-known quantities, but novel quantities seem to pose some different problem, but I didn't quite get that. I'm sorry. Can you please repeat it?
Yeah, so the idea is that if you take a more traditional line on what does it mean to interpret general relativity, and say you think that what we have is a few principles relating, geodesics to certain types of particle motion or null geodesics to light, those sorts of interpretive principles, you could imagine sort of saying, here's the novel mathematical physics of GR. We have the principles to relate them to something else. And then from there, we pick up and tell the story about how we schematize the observers in order to understand how those principles will allow us to connect the mathematical physics with the ultimate story about, looking at the planets and seeing their trajectories. So the claim would be, is there something wrong about that picture where you introduce novel quantities and you have to do some interpretational work that could look like, the kind of way that Malaman specifies how we should interpret GR. And then from there, you go on and see how you schematize the observer, or there's a different claim you might be making, which is even in that step, there's a way in which you schematize the observer, even in understanding, say, the relationship between general relativity and the first of this long chain of theories that has a distinctive character that philosophers have missed, and that we need to schematize the observer in a way that leads us to rethink even that.
Okay, good. So I do not want to claim that in any philosophical investigation of the content of the theory or what it means for a theory to have content, you always have to produce a schematization of the observer in some particular experiment. I think that has to be there in the background in principle, and one should be able in some sense to call upon it as required. But in many cases, we understand the theory so well, we understand the interpretation so well, we understand how it relates to the world so well, that it would be OTO to say, oh, and by the way, here's how you explicitly model the experiment, the experiment for studying this kind of quantity. And you mentioned Malaman. A beautiful example of this is Malaman's work on how different senses of rotation that all agree in classical physics come apart in general relativity. I mean, he actually does schematize the observer in those arguments, but again, the observer just is lines of sight, null geodesics in this case. So, and I mean, he doesn't call it that. I'm not even sure he thinks of it in that way, but I think that's what he's doing. So, and again, a lot of work one can do in explaining the physical content of Navier-Stokes theory and what it means to be a theory of fluid dynamics. You can explain an extraordinary amount of the empirical content of the theory without ever mentioning the word experiment, without ever mentioning the word observer, without ever mentioning, you talk about the fluid itself, so to speak. But at bottom, at the end of the day, if you really want to claim that what you're doing is talking about the empirical content of the theory, when push comes to shove, you have to be able to show how this connects to our understanding of how it is that we represent and treat real experiments. Now, the issue about novel theories and novel quantities or novel structures or principles that new theories introduce, I think that's a really interesting question, and I think there it's actually deeply important to schematize the observer when these novel things are happening. Think about, Einstein's long struggle with the equivalence principle between like about 1908 and 1915. He was constantly proposing experiments in order to try and understand what the equivalence principle meant. They weren't experiments he expected to perform. They were thought experiments, so to speak. But he was constantly trying, in order to understand what consequences the equivalence principle should have for an adequate theory of gravity, he was constantly coming up with new experimental situations in which one could probe, so to speak, the meaning of the equivalence principle. And it was only after I think he really satisfied himself in that way that he feel like he had a good grasp on what the equivalence principle meant, and then he was able to use it and apply it in later work without mentioning explicitly all this work he did at the beginning that was essentially modeling experiments to try and understand the content of the principle. So I do in fact think that there is a difference. That when new theories come up, when novel quantities or novel phenomena are introduced, I think it really is that is when it is most important to be able to have a good grip on how it is that we can actually study these systems under some kind of, maybe not controlled circumstances, but at least observation.
Thanks.
Nick?
Actually, there's a couple of questions. Can you hear us?
Yeah.
Okay, Sakshi first, but I have one too.
Hi, Erik. Thank you for the
Hi,
talk.
Sakshi.
So I really enjoyed this because this is one of the few talks I heard not about black holes. So it was nice to hear your perspective on something else. And one thing that I am still confused by is how the theories of experiments or observers are not subject to the same standard view dilemma, in that there seems to be a large gap between the realistic complexity of the actual physical system and the simplified model being used to represent them. And as you pointed out, it seems to only be traversable by a leap of faith. And in some of the examples you gave, for example, astronomical observations, it seems like we are using these very theories for which we need to make the leap of faith to model or schematize the observer. So I was wondering if you could say a little more about that.
No, that's a wonderful question. Thank you. So it is the case that instruments and instrumentation and how they're designed, how they're built, how they're deployed do involve quite a lot of very often a very deep and profound theory. So again, you're just thinking about the telescope or the microscope, how much knowledge of light and optics is required to understand how those instruments work and how they can be meaningfully used. So I mean, when you always have to, we're finite beings. You always have to take something for granted. You always have to take something as given. To get any kind of research program off the ground, to try and tackle any kind of problem. And when one wants to try to schematize the observer in a theory that one is studying, one often will rely on very simplistic models of the instrument, and very often that's all one needs. But sometimes one really does have to get down into the details of the theory of the instrument. And there are a variety of ways of doing that, because there are a variety of ways of treating and modeling a system in what we more normally think of as a theory, like general relativity. There's a really beautiful paper by James Clerk Maxwell called "The Theory of Optical Instruments," in which he actually works through, both in the abstract and in rather detailed discussion, what exactly is required for an optical instrument to be a good optical instrument for various purposes, and what theory we need to have in place in order to guide the design of optical instruments, and how it is that we should then use the optical instruments in order to constrain our theorizing. So sometimes you really need to get down and dirty with the theory of the instruments in the way that that Maxwell did in that paper. Sometimes all you need is a line of sight. If you're in the 1670s and constructing the ephemerides. I don't think that there's a clean and principled distinction. There's a clean and principled line to draw about when it is you need to do which. Like so much in science, it really is a case of having a feel for what's needed and when, an intuition that you've developed. That it's not the pure philosopher's intuition. It's an intuition that you've developed over many years of experience and practice with the theoretical machinery, with the experimental instrumentation and design. And to hark back to Sebastian for a minute, it's what Duhem called the physicist's good sense. I think is what is needed very often. So I feel dissatisfied with the answer that I gave you. Is there more on some particular point that you'd like me to say?
So just as a quick follow-up, if I understood you correctly, because it can't be turtles all the way down, you need to take something as a given. It's okay, for example, when we're interpreting general relativity, that we schematize the observer using, say, Newtonian physics. But then in another context, if it's Newtonian physics of the theory in question, say for planetary motion, and we need a theory of optics to schematize the observer, the same theory can perform the role as the theory of the experimenter or as the theory that needs to be supplemented by another such model of how you schematize the observer. So am I understanding correctly that the same theory, depending on what role it's playing, can be both the one that's subject to the standard view dilemma or the one that is performing the role as schematizing the observer?
Yes, that's exactly right. When you're dealing with GR and you need to model a telescope, you can almost always get away with doing it rather crudely. If you are really thinking about the telescope if you really need to get down and dirty with the details, then you might need to start calling upon the resources of metallurgical theory, of other theories of condensed matter, of glass, of meteorology, and you need to be able to, the question of when you need to schematize the observer in order to be able to meaningfully apply a theory is one that has no determinate answer once and for all.
So the same theory can be the one that, is either at risk of requiring a leap of faith, or the one that's saving you from that risk of making the leap of faith. The same theory can, have both characteristics.
I think that's right, yeah.
Okay, excellent, thank you.
So may I?
Yeah, sure.
Thanks, Erik. I mean, this was a great talk, as always. And I agree with lots of this. My question may just really have to have the same answer to Richard's, that you need to send the manuscript to properly answer it. But let me try it another way, which is, I'm again thinking about connections between what you're saying, what people have said, and other philosophers have sort of suggested in the past. I think the kinds of things you're saying I associate in the past with debates about not about semantics, but more about realism and sort of moves that have been made in the realism. So I guess that's what I want to kind of ask you, if you can say anything about, does your view leave room for sort of a realism, anti-realism debate, or is it supposed to sort of just get rid of that? Because you can sort of see the way the bold statement of how you put it, it sounds like there's a danger that all this semantics, it's some kind of fancy verificationism, something like that.
No, that's a very fair question, and in fact, one of the overarching goals, one of the overarching aims or constraints, I'm not sure what to say, that I placed on myself in trying to think about these issues is that everything, I would like it to be the case that everything I say is completely neutral with regard to the realism, anti-realism debate. I really don't want to take a stand on that. I think at least not the way that the debate is most usually formulated in, by the most influential works. And I think that so I do, and I mean, when I say that semantics, shouldn't be fixed by Steining City of Ontology on the Hill, I mean that it shouldn't be fixed only by that. And in fact, to me, so I'll say a tiny bit about my own view of semantics, the one that I'm trying to develop, which is to me, this view of semantics based on ontology is forced to take designation or reference as the fundamental semantic relation. To me, a designation or reference may be very useful in many ways, but it's always a derived relation. And precisely because in order to get reference and designation off the ground, we first have to know what the systems are that theory meaningfully treats, but that requires an enormous amount of what is normally thought of as pragmatic knowledge in order to demarcate that class of systems. So however it is that meaning is supposed to accrue to the terms of a theory, I don't think it can do so by reference or designation as the fundamental relation. Now, I guess having said that, in that way, I guess I would want to reject. I guess if you find my position plausible, or the ideas and arguments I'm making as at least interesting enough to follow up on, then that would strongly suggest that a lot of traditional ways of formulating a realist program are misguided. But those from the 70s, like the ones that Putnam was talking about, the semantic realism, so the kind of realism that Bas van Fraassen talked about, because that picture of realism really does depend on theories being, in some very strong sense, a kind of designative or depictive, representation of the world, and I want to push back on that. I think we do learn very important things about the world from our theories, but it's not because our theories are designative or depictive pictures of the world. So I guess at the end of the day, I want to say I would want my account. I'd want my ideas and account to be neutral with regard to a more sophisticated formulation of the realism anti-realism debate, one that doesn't depend solely on ideas of Tarskian semantics or Beck semantics or possible world semantics, or any semantics that reduces the entire semantic relation between theory and world to one of designation or reference or depiction.
Okay, thank you.
We have one more question by Sebastian.
Yes, basically, I'm wondering about your dislike of reference, and the reason is that I can see that one would like the idea that one dislike the idea of us having an idea of what, I don't know, the quantum field is or so. We think of sort of, we have the wave function, and the wave function points to a thing in the world. The function itself that we write down points to a thing, and there it is. That's realism or something like that. But this is basically, that's starting from the theory, right? Mm-hmm. And you just said that you want to start from sounds to me like you want to start from the observer to figure out what our theories mean, in a sense. And reference on the observer level seems to be completely fine and possibly even necessary. So because this tends to be how we think about stuff, right? Sort of, if I want to, the line of sight or so, I want to talk about that telescope, right? And I want to talk about that line of sight, sort of, I want to be able to point at something or something like that. And on that level, reference seems to be just fine. It's just sort of just the idea that you can first have the reference of the theoretical concepts, and then afterwards sort of connect it in some way. Yeah, it doesn't really matter to observation. That's the misguided part. It's not the reference itself. It's just that it is associated with the wrong thing, basically. So I'm sort of the more you talked about your view, the more I was wondering how close it is connected here to this. I mean, you might remember this. I have this book that I want to sell to everyone, Marian Trewanski's Logic of Empirical Theories, where he basically uses exactly your standard Tarskian semantics and just says, well, what about we don't assume that our theoretical terms refer to this thing and then see what happens. But instead we say, well, we have our sentences that we think are correct, like the equation. Yeah, we have our equations that we think are correct. Then we have a description of the observational methods, also in some sense formalized or schematized. I mean, he assumes that it's all in first order logic because that's what's doable for him at that point, and then says we would want to generalize this to other logics and all math and all that. Yeah, and then sort of starts with Tarskian semantics and then just sees how it all becomes hazy in the more theoretical term. But at the observational level, he's completely fine, right? So he just uses Tarski semantics, uses designation and reference, and then things become very, very much non-realistic, non-referential, or at least non-referential in the theoretical realm. And that seems to be completely compatible with what you're saying.
So, so first of all, the only reason I know about Przewalski and that book is because you told me about it, and you forced me to read it, and I really loved it. And in fact, I really do think that is great stuff, and I think that there is some real commonality between what he talks about and what I'm trying to argue. But I would say that a few points. One, the idea of reference is always embedded in a theory of semantics. The idea of reference itself is a theoretical idea. And if we're going to use reference in order to try to account for the empirical content of theories and how it is theories make contact with the world, then that we have to be clear on what the theory of reference itself is. And we also have to be clear that, like every other theory that I know of, not just scientific theories, but in this case, say a philosophical theory, it has its own regime of applicability. Theories of reference are sometimes really useful and applicable and adequate and appropriate for use, and they're great. But they so to speak, they break down sometimes. They really are inadequate and inappropriate in many contexts. So the idea of using reference to talk about the observer and observation, I think that I wouldn't be opposed to it, again, as long as we were careful about when, where, why, and how we applied the idea. So here's an example of the kind of thing I'm worried about. In my favorite example, the water. So in this state, it's relatively quiescent. So the pressure of the water is well defined as a quantity. In the sense of Navier-Stokes theory, what Navier-Stokes theory means by pressure, completely well defined. When I start to shake it, as the water approaches turbulence, the Navier-Stokes equations of motion, the dynamical equations, they very quickly become predictably inaccurate. They can't handle turbulence. But a lot of the kinematical formula and relations and equations, things like the shear stress tensor must be symmetric, heat flow is independent of pressure gradient, all these kinds of fixed relations that every Navier-Stokes theory must satisfy, those actually continue to hold. And we can use those to characterize pressure and measure pressure, even when the dynamical equations fail. But it's pretty clear that whatever it is that we're referring to, whatever it is that pressure means, in that case, can't be straightforwardly, I think, the meaning can't be exhausted by reference there, because you have to be able to tell me why it is that the P that appears in gradient in thermal flux is independent of pressure gradient, why that's the same P as appears in one of the Navier-Stokes in one of the dynamical equations that fails. And so I think that in that situation, reference is too coarse-grained a semantic relation to allow us to understand what's going on. But in a lot of other cases, that aren't so kind of tricky and delicate and complex, it works great, and we should avail ourselves of it. It's one more tool in our toolbox that we should feel free to use when we have done the work to ascertain that this is the context in which it is appropriate to use that tool. But in any event, I don't think it ever can serve as a fundamental semantic relation, whatever exactly that means.
That sounds great. Yeah, thanks.
All right, so if there are no other questions, let's thank again Erik for the seminar and for taking the time to answer all the questions.
Well, thank you all very much for joining and for the great feedback. Thanks, Doc.